Sorry, I lost my mic for a second. In this video, I would like to go over how to do the arc length problems in the homework. I'm going to make a few others. Rather than making them 40, 50 minutes long, I'm going to shorten them a bit. So this is on 6.5 stuff from the Briggs book. Typically, these, in a regular course, these would be considered pretty difficult, and we would spend a lot more time um, on doing these. But our course is fast paced, so um, you can get pretty crazy with these. We only have a couple questions though, so there's no need to go super in depth with arc length. So from the book, the formula to find arc length is given by the antiderivative from the endpoints a to b of the square root of 1 plus dy dx, or uh yeah. Okay, so that's what it looks like. Let's talk about arc length. Is if um if we had a curve, let's say, and you may have seen this formula in trig, right? If you remember in trig, you could find arc length from r and theta. So if you wanted to find, like, say, from here to here, do you remember what the formula was? It was r times theta, right? And you can find area of sectors similarly, but we are not really on a circle here, right? We're not always in a circle. That formula kind of is limited to circles. So imagine we're in Cartesian coordinates and we have some curve. So far, we've been focusing on area and volume, but we can also calculate the length of the curve, right? So we're kind of almost in the physics realm here, but not quite. Um, Anyways, so it's given by this formula. It doesn't get as complicated as, could be, but like I said, let's just get these done. So we have our function y in this example, and you might notice that we have fractional exponents. And typically, we're going to be dealing with exponents that are going to give us trouble, right? So our function y is 2x to the 3 halves. Okay. Take the derivative. Like, all this formula says is, if you have the endpoints, which we do right here, we're going to add 1 to whatever the square of the derivative is. Again, we're going to ignore the fact that we have annoying exponents, but every problem is going to have those. Okay, so y prime, or dy dx, however you want to call it, is 2 times 3 halves. What's our new exponent? 1 half. So this is equal to 3x to the 1 half, or 3 rad x, however you want to write it. Okay, so that's our y prime. This formula says we have to square that. So what happens if we square this? We would get 9x. Okay, so our arc length is going to be, I'm going to write it here, and then we'll get rid of all the other stuff. The integral from 0 to 7 of the square root of 1 plus 9x dx. Okay. All right. Now, some of you have mentioned, oh, you forget how to do U sub. Well, this is good practice, and practice these. So let me erase some of this. All right. So if you got the setup, if you get to this point in the problem, that's awesome. Okay. So this is a U substitution where we're going to let U equal 1 plus 9x. Okay, so when you get du from that, du is 9 dx, right? Derivative of 1 is 0, derivative of 9x is 9, and we have dx. So right now our substitution looks like this. Antiderivative from 0 to 7. I'm not going to change my limits because I'm going to change my u back to x. So um, so I'm not going to plug these in for x and get my u endpoints. So, um, this is u, right? We said let 1 plus 9x be u. Now here's where it gets tricky. We have a dx, so just like we substitute this to be u, we substitute for dx. But to do that substitution, we have to have dx by itself. So du is dx, but we move the 9 over here. So we have du over 9, but I'm not gonna put the 1 over 9 here. I'm gonna put it out front. Okay, because it's multiplied, I can move it. Okay, so let's erase this and see what we got. Okay. We got, well, we think of this from powers, right? If you remember, at this point in the class, we really only know how to use the power rule for exponents. So we think of it as this, du, and then according to our rule, we add 1 to that exponent. So this becomes 1/9 u to the 3/2. No more du, that's gone, we integrated. Plus a constant, but we don't need that because it's a definite integral. Okay. And this is evaluated from 0 to 7. But before we plug it in, we have to remember that our u was 1 plus 9x. So we have 1 plus 9x to 3/2 from 0 to 7. And then you can see if you plug that in, oh wait, sorry guys, I forgot to multiply by or divide by 3/2. Divide by the new exponent, so that's the same as multiplying by 2/3, which gives me 2/27. So we have this. There we go. Okay. So now when I plug in 0, let's move some stuff around. Yeah, I saw the answer choice. So I was like, wait, we missed something. So now we have 2/27. When I plug in 7, I'm gonna get 1 plus 63 to the 3/2. And I plug in 0 the same way. 1 plus 0 is just 1. Doesn't matter really what power, it's still gonna be -1. And you can see that 63 plus 61 is 64. -1. I have 2/27 out front. So you just figure out which one that matches. It's clearly this guy. Okay. I didn't realize I already done that, but yeah. All right. So that's first arc length problem. Second one is a little trickier. So you might get the first one. You might be like, okay, I got this. It's easy. And then you try this one, you're like, oh my gosh. So um, as one of my colleagues said, these are set up to work out perfectly. So the technique I do is not some sort of like not some sort of like magical like cure-all technique. It only works for the problems that we're given. Okay. So make sure you make sure you understand what I'm saying. Just because you see me do this doesn't mean it's always going to be this easy. Okay. I just know these work out, and there's really only one way to do it, and it's exactly how you'll see. So again, we need the arc length formula. It's yes, like antiderivative from a to b, square root. This time let's just call it y prime. In other words, the derivative of this. So before we start, we take the derivative. 4 comes down, it's going to be x cubed because the 4's will cancel here. And we think about this one, if you recall, we could think of this as 1/8 x to the -2. So when I take the derivative of that, I have -2/8 x to the -3, okay, which is really just this, -1/4x to the third, like that. Okay. So also this gets squared. Let's make sure we have the right formula. All right. So before we start plugging in, remember we have to square this. So there's no easy workaround, right? We gotta get rid of this. We've got to uh, square this, which means FOIL. Uh, okay. And if you FOIL that, just remember it says y prime squared, you would get x to the 6 when you do these two. When you do these two, you got plus, let's put it over here, 1 over 16 x cubed. No, x to the 6, sorry. Now, when these two get multiplied, so when we do this and sorry, not that, that and that, we're going to get minus a fourth, and check that. And that combines to be minus a half. Here's the tricky part, and these problems just work out perfectly. In other words, they're sort of the same algorithm. If we slightly change this, we wouldn't be able to solve these. Okay, so we're limited here. X to the 6 minus a half plus 1 over 16x to the 6 plus 1, which is this. Now, the negative half and the 1 make it positive 1/2, and we have this. So let's erase some stuff and talk about how this would go if we didn't know what to do. Okay, so let me break down sort of the thought process here. So where we're at, and the arc length formula is an integral. Um, we have this from 1 to 3, square root. We already added the 1 to the derivative squared, so we have everything we see. X to the 6 plus a half plus 1 over 16x to the 6 dx. Okay. We could stare at that for hours, and that's sort of the downside with these. We could stare and stare and stare, nothing's going to happen. But we want something to happen, right? We want to be able to get this thing right. So we kind of think this way. We're like, well, we have a square root. We don't have anything in our power or toolbox to be able to integrate this. We only really know u sub at this point, or power rule. You could try to think of clever ways, and that's awesome, but nothing will really work, right? There's no way around it. Sorry, student emailed me. Okay. Anyways, so we think, okay, the only way we can get this integral to work is if we didn't have a square root. And if you notice, the arc length formula has a square root built into it. So um, you can't really get around that, right? There's a square root, unless we have some perfect formula that works out, can't get rid of it. So what we think to ourselves is, well, if we had something inside the square root that was squared, we could get out of the square root. So it's not obvious as it's written. And once you do this, you'll see that it's the same pattern every single time. It turns out, so here's the hand waving trick. This thing right here is in fact something squared. And it's something plus something. So look carefully. What plus what would give us this thing if we FOILed it out? And you might say, well, we just FOILed it out. We did. When we FOILed what we had out, we got this. But when we add this little 1 here, it makes it a positive graph. So it's a different thing, right? As it turns out, remember what we FOILed here to get this? We did x cubed plus 1 or minus, and that's the kicker right there, minus 4x, 1 over 4x cubed. So it turns out if we change that to a plus, we would get this. And you can check that. So if you squared this, you get this, which is what we have. So we do in fact have something squared in here, and it's this. Now, You can think about this all day for hours, but you just have to believe me that it always works out that way. Okay, so the trick is it's right here. Well, we initially FOILed out when we took the derivative and squared it. We FOILed, let me get rid of that little FOILed, FOILed this. What happens is all we're doing is changing that negative to a plus. Okay, and it magically works out, hand waving that would give us what we have, which is inside there. So what we really have here is a square inside a square root. And if you know from any algebra course, they cancel each other, right? So we can um, we can get rid of the square root. Let's rewrite it like this. So we really have this. Okay, dx. And then you integrate that accordingly and plug in. Okay, so that's how you do that one. I think that's the last arc length problem, so I hope this video helps. This is 6-5. I got rid of a bunch of problems, guys. They were just too complicated. Moving forward for the next few homeworks, I'm going to be making them. Um, so we're just going to do 6-5, and we're not going to do 6-7 because the problems are not really helpful. So that's all I have. If you need help with any of the stuff from chapter 6, let me know. And the next videos will be in chapter 7. Thank you.